is our lecture number 21, and today we are going to discuss deadlock prevention methods. This is our lecture number 3 of deadlock chapter. So from our earlier session we have discussed basic things about the deadlock and resource allocation graph and deadlock recovery. Today we are going to cover up the deadlock prevention. So just to give you a brief about it, what are the various list of conditions for a deadlock to occur. So for a deadlock to occur, there are 4 conditions, namely mutual exclusion, hold and wait, no preemption, and circular wait. So for a deadlock to encounter or for a deadlock to occur by the system or in the system, all these 4 conditions has to be simultaneously occur. Okay, or all these condition has to occur simultaneously. Fine. Okay. Now let me give you a brief about what is mutual exclusion. Mutual exclusion means whenever there is one process that is accessing a particular resource, okay, and that resource cannot be used by some another process, right? So resource has to be used in an exclusive or mutual exclusive manner, so one at a time. Next is the hold and wait. So hold and wait condition, it states that whenever there is a process who wants to use some resource or who is requesting for some resource or who is waiting for some resource to get free, it's holding at least one resource. So basically the condition says that there should be one process in the system or in a deadlock scenario where it is holding one resource and is requesting for some additional resource which is not been allocated to the requesting process because it has been assigned to some another process. Right? And no preemption. No preemption means the process has to release the resource that it is holding voluntarily. Okay, voluntarily, or in other words, implicitly. So these are two very important words: voluntarily or implicitly. So nobody can snatch the resources from the process. Okay? So the process has to release the resource voluntarily. That's why no preemption. Okay? Next is the circular wait. So the circular wait condition states that there are list of process and there are list of resources who are entangled in the deadlock situation or maybe in a cycle fashion. So whenever they are entangled in this cycle fashion, the process and the process and the resource are entangled in this highlighted manner. Like for example, the resource R0 is assigned to P0 and P0 is requesting for resource R1, whereas R1 resource is assigned to P1, but P1 is requesting for R2. Like that way it will continue. At the end, the resource Rn is being allocated to process Pn, whereas Pn is requesting for resource R0. And they can see there is a circular sequence. This kind of circular sequence is known as a circular wait scenario. Okay. So all for a deadlock to occur, all these 4 conditions has to satisfy at the same time. But we are here to discuss the deadlock prevention. So as I've told you just now that for a deadlock to occur, all these 4 conditions has to be satisfied simultaneously at the same time. Now if we can impose some rules on these conditions, right? I repeat, if we can impose some rules on these conditions, or if we can impose some protocols or rules and regulations on this condition during the process execution, and if you try to fail any one of these conditions, then we can say that we have broken the deadlock, or we have prevented the deadlock situation to occur, because we have imposed rules on any one of them. Okay, we have imposed rules on any one of them, and by imposing that rule, the corresponding condition will fail. The corresponding condition will fail. I repeat, we are trying to develop a protocol or a regulations or rules for implementing it in the system. If we implement the protocol, okay, any one of the condition, if you try to implement, there will be a different protocol we can use it. Suppose we may if you try to impose any one of them protocol and try to make the system fail or try to make the deadlock situation fail by failing any one of these conditions, then we will be successful in preventing the occurrence of deadlock. So that's why I have highlighted in this red portion. By ensuring that at least one of these conditions cannot hold, okay, we can prevent the deadlock. So how can we prevent the deadlock, or what are the various protocols that we can impose on these different conditions so that the condition becomes fail or the condition fails? So we'll look into it one after another. Okay. First of all, mutual exclusion. So whenever we are trying to make whenever we are trying to impose some rules on from a mutual exclusion point of view, okay, I repeat, we are trying to impose some rules on mutual exclusion so that mutual exclusion fails. What we can do, or what is the possibility we can do? Suppose we are trying to impose rules on mutual exclusion, then we can put a condition that mutual exclusion condition must hold for non-shareable ratios, right? For example, actually in the system there are two different kinds of resource. One is shareable resource and the one is a non-shareable resource. For example, of non-shareable resource, suppose you have a printer. Okay, suppose you have a printer and you have the document to print it. Okay, you have the document to print it. You have a printer and you have the document to print it. In the document there are, say for example, line number 1, line number 2, line number 3, line number 4, line number 5. Okay? So there are 5 lines in the document and you have given the print command. Okay, you have given the print command to the printer. Okay, this is a printer. Okay, this is a printer. You have given the print command to the printer. It has to print. Now, whenever you give this command, print command to the printer, okay, it is not happening that this line and this line is get printed, and after this line, these lines are not being printed. It's not happening that. Either it will print all, or either it will print none. Okay, I repeat, all or none. I repeat, all or none. So either it will print all the lines, okay, or it will not print any of one. So printer, this kind of resource is known as a non-preemptible resource or non-shareable resource, right? So non-preemptible resource or non-shareable resource. That's what it is talking about. So we can apply this mutual exclusion in a scenario where there are only non-shareable resource of type a kind of printer. But in a computer system you have got other different kind of resource as well. Like for example, computer memory, right? Suppose you have a computer memory or a file. Let us talk about a file, okay? Suppose there is a file. Suppose there is a file. There is a file. This is a file. F-I-L-E, file. And the attribute associated with this file is read only. So the attribute associated with this file is what? READ, read only file. So this is a read only file. So suppose there are multiple processes. Suppose there are multiple processes P1, P2 and P3 who is sharing this file. Okay, who is sharing this file or who is reading this file at the same time. So there is no harm. There is no harm in this. Okay, it is not going to create any kind of problem. So that's what it is talking about. There are two different kind of resources in the computer system. One is the shareable resource of type printer, and another one is non-shareable resource of type printer, for example printer, and another is shareable resource like read-only file. So you cannot apply the rules of mutually exclusive access to read-only files. It's not happening that you will try to apply the okay, this file has to be read by only one of the process at a time, although it is a read-only file. It's not happening that. Okay, you cannot change the attribute of this. Okay? So it's very difficult to impose make this mutual exclusions condition for. It's difficult. It can be applied in a scenario where there are only non-shareable resources, but in a computer there are shareable resources also, non-shareable resources also, and process may demand any one of them. So it's very difficult. So that's why I can read it out here. In general, however, we cannot prevent deadlock by denying the mutual exclusion condition, as some resources are intrinsically non-shareable or shareable. Okay, fine. So there might be in a computer system, there might be some resource whose property cannot be changed. Like for example, you cannot change the property of printer from non-shareable to shareable, or there may be some resources type shareable which you cannot change it to non-shareable, right? So it's very difficult to make this mutual exclusion condition false. So it is generally, whenever anybody is trying to implement it, it's generally avoided. So you don't impose rules on mutual exclusion. But however, the remaining three conditions, we have certain sets of rules which you can impose it or implement to make the deadlock condition to become false. Okay? So we'll go one after another. So say for example, now next condition is hold and wait. Okay. So what do you mean by hold and wait? First we'll try to explain what do you mean by hold and wait. Okay. Suppose there is a process P, okay, and suppose there is a resource R, okay, R1, and there is a process P1, and there is a resource R2. I repeat, in a computer system, suppose there is a process P1, there is a resource R1 and R2. Now hold and wait means P1, R1 is assigned to P1. R1 is assigned to P1 means P1 is holding R1 and P1 is requesting for R2. P1 is requesting for R2. So you can see the arrowhead. R1 is from arrowhead is going from R1 to P1. So basically it means that R1 is an instance of R1 is assigned to P1. Whereas here in this case, second arrowhead is going from P1 to R2. Okay, so which means that it is a requesting. P1 is requesting for R2, whereas R2 is assigned to some other process, which is of not Y. So this scenario is known as a hold and wait. So how do you impose a rule on this scenario? Okay, how can you make a rule on this scenario? How can you impose a protocol or a rule so that this condition will fail? If this condition fails, then very obvious that the deadlock condition will not occur due to a failing of hold and wait condition, right? So to ensure that hold and wait condition never occur in the system, we must impose a rule in such a way that whenever a process requests a resource, it does not hold any resource. So say for example, there is a process P, okay, and there is a process P who needs the resource Ri. Okay, suppose there is a process P and who needs the resource Ri. Now you impose a rule on the system in such a way that whenever any process wants to request any resource, it should not hold any of the resource Rj. Okay, it should not hold. If you impose that rule, such kind of rule, then obviously hold and wait scenario will not occur. Okay, I repeat, if whenever in a system you try to impose a rule, okay, suppose there is a process coming up with the request of resource. So P is demanding for printer. P is demanding for printer, right? So system before assigning the printer to P, before assigning the printer to process P, the system will check whether the P is holding any one of the resource. If not, okay, or you will allow the assignment of printer to resource only when it is not holding any one of the resource. So this, if you impose this rule, then things will be easy for this hold and wait condition to fail. Okay, so for this, for hold and wait to get disqualified, or for hold and wait condition to fail, we have got two protocols. Okay, we have got two protocols. First protocol, it states that first protocol says that each process to request and reallocate all resources before it begins the execution. I repeat, okay, I'll just explain the same thing with the help of the example. Suppose there is a process P. execute this process P needs printer. Okay, so I'll write R1 is your printer. It needs so for example disk, hard disk. Okay, so I'll write it R2, and it needs keyboard or pen drive. Okay, pen drive, suppose R3. So to execute this process P, or the instruction that is inside the process P, it needs printer, it needs pen drive, it needs printer, it needs pen drive, and it needs maybe disk, hard disk. Okay, yeah, some memory, computer memory. So having said this, so all these three resources is required. So before the process P started execution, all these resources has to get assigned to P. Then only it will start execution. EX. So process P starts its execution only when it is assigned with all these resources for it to initiate or for it to complete the task. That's what the first protocol says. One protocol that can be used for this process to request and reallocate all its resources before it begins the execution. Okay. Now, it might happen that the resource R2 is used at the last time. Okay. So first, initially, the data. Suppose the job is to read the data from the pen drive. This R3 is pen drive. I repeat, R3 is pen drive, R2 is disk, and R1 is printer. Suppose the job of this process P is to extract the data from the pen drive and store it into the disk and do some management over here, and then later on at the end you print the data, okay, modified data. Suppose this is the task. Now to do this task, suppose it might happen that for reading and for writing, so it needs R2 and R3. For reading the data from the pen drive and writing into the hard disk, so it needs R2 and R3. So it might happen that it will first request for R2 and R3. Then after completing the task R2 and R3, it will release the resource. It will release the RELEAS. It will release R2 and R3, and then after that it will again request for R1. So it might happen. Okay, it can follow. So this is the second protocol. So alternate protocol allows the process to request the resource only when the process has none. Okay, a process may request some resource. So basically, initially R2 and R3 is requested by P, and it is not holding at that time. Whenever P is requesting for R2 and R3, P is not holding any one of the resources. Okay, so initially, suppose I'll just copy it. Control X, Control X, Control X. Suppose to execute the process P, it needs R1 and R2 and R3. R1 is printer, R2 is disk, and R3 is pen drive. The job is to copy the data from the R3 from R3 pen drive to hard disk and do some management over here. And at the end, you print the data. Okay, with the help of the printer. That is resource R1. Suppose this is the task. Now initially P can do what? P can request for R3 and R2, okay? So that it needs to copy data from R3 to R2. So after copying the data, what will happen? It might happen that these two resources will get released, and then it will request for R1, and then that R1 is assigned to P. So this is the sequence. Okay. So a process may request some resource and use them, and before it requests any additional resource, it must release all the resource that it is currently holding, right? So this is another protocol that you can apply in the computer system to make the hold and wait condition false, right? So I'll just give you a revision of it. So in order to make the hold and wait condition false, there are two possible protocols that you can apply into the system. First protocol is whenever the process starts its execution, it will try to get allocated all the resources that it needs before beginning the execution of the instruction. Okay. That is one thing. Next protocol is whenever a process requires some resources, it will request it, okay, and then use it, and after using it, it will release it. Okay, whenever any additional resource is required, okay, it will again make the request. After using all the resources, again it will release it. So that thing one can be done. So if you are getting confused with the these two protocols, I would like to give you one example, okay, that will make the clear difference between protocol 1 and protocol 2. Suppose there is a resource R1, R2 and R3. Okay. So R1 is your printer. I am taking help of same example so that it becomes convenient for all to understand. R2 is your disk or hard disk, let's say, and R3 is your pen drive. Okay, so now what is your job? The job is to copy data from pen drive to disk and do some sorting. After that, print the sorted data. Okay, so this is your job. So the job of this process P is to copy the data from R3 pen drive to disk and do some sorting, maybe increasing order of student names or decreasing order of student names, address, etc. Then after doing this, okay, print the sorted data with the help of the printer. So to do this task, it needs three resources: R1, R2 and R3. As per the protocol number 1, what will happen is that P will make the request for R1, R2 and R3. So requesting is going from process to resource. Now it should be assuming the fact that R1, R2 and R3 are free. What will happen if it is free? So it will get allocated to R1 will get allocated to P, R2 will also get allocated to P, and R3 will also get allocated to P. So after allocating all these three resources, P will start its execution. Although printer will be used at the end, it will be held by this process for a long amount of time until and unless its sorting completes. So basically printer will be used at the end. So once it does all the tasks, that is copying the data from here to here, R3 to R2, will sort it and then again it will print it. Okay. So after completing all the tasks, it will release all the resources. So that is the first task. So whenever a request is made, it is also checked that P is not holding any additional resource. So P is only entitled. So P is entitled to receive. P is entitled to get this resource R1, R2, R3 only when it has none of the resource that is assigned to it. So this is first protocol. Second protocol says that based on the nature of the task, so it will first make the request for R3 and R2, because first phase is to copy the data and sort it, which requires some time. So P will be requesting for R2 and R3 and then start executing. Okay, it is not awaiting. So now this condition is also P is allocated with R2 and R3 only if R2 and R3 is free and none of the resources are assigned to P. Okay, so none of the resources assigned to P. So after P gets R2 and R3, it will do the task, copy the data from pen drive to disk and sort it. After sorting it, what it will do, it will release it. Okay, it will release this task, or it will release this resource. Then after that, it will make the request R1. Once it makes the request R1, again the same condition is checked whether it is holding or not if it is not holding, okay, if it is not holding, then if it is not holding and R1 is free, then R1 is assigned to P. Okay, so it can print it. So this is your second protocol. So I hope I had made it clear difference between the first protocol and second protocol. I'll just read it out. Second protocol: an alternative protocol allows the process to request the resource only when process has none. That is very, very obvious. A process may request some resource and use them and before it requests for any additional resources, it must release all the resources that it is currently holding. Okay, so this is another protocol that you can use. Any one of them you can use it. So however, in case of the first one, like for example over here, in case of the first one, if you have applied the first protocol, then it is seen that printer is used at the end. So printer is used at the end. So till the time it gets completed, copying the data from R3 to R2 and then sorting. Say for example, it takes huge amount of time. So till that time, printer is just engaged. Okay, so it might happen that printer could have been used by some other process for efficient utilization of resources. It might happen that. So, but this is due to this, it's not happening, right? So it might happen that one of the problem is low resource utilization. So although the printer was used at the end, so it could happen that low resource utilization. It could happen printer is not utilized efficiently. Okay, so one disadvantage is that. So another disadvantage with any one of them is starvation, or second one is starvation is possible. Okay, because the common resources are frequently used by the many resources. Okay, as for example, printer is very, very common resource. So it might happen that some of the low priority process may not get a printer every time whenever it is demanding. So some of the process, due to some nature of the process property or attribute, some process may starve for some resource because some of the commonly used resources are frequently being allocated to high priority process. So this could be the one reason. So I just repeat it. Okay, hold and wait situations. The main problem could be, the disadvantage could be a low resource utilization and starvation problem. Okay, or starvation is possibility of starvation. Right. Now, next is the no preemption. No preemption means, as a name suggests, you cannot preempt. So you cannot preempt means whenever a process requests for some resource, whenever there is a process, okay, whenever there is a process P, okay, and it is requesting for some resource R1, okay, and assuming the fact that R1 is free, so R1 is assigned to P1. Now in that case, after P1 gets resource R1, it will try to execute by using this resource, okay, and during the execution of this resource, nobody can take away the resource from this process P1. That is the meaning of no preemption. It means that there will be no preemption of resources that have been already allocated. So this is the meaning of no preemption. Now you need to think, how can what rule that I can impose on the computer system such that this condition is will be failed. Okay, what kind of rule should I apply? Okay, so what kind of rule should I apply such that this condition will become failed? Okay, so to ensure that this condition does not hold, we can use the following protocol. Okay, so I'll just read it out and then explain it. If a process is holding some resource and requests another resource that cannot be immediately allocated to it, then all the resources currently being held are preempted. Right? Okay, I'll just explain you. Okay, suppose there is a process P1. Suppose there is a process P1, okay, at time t equals to maybe 10 millisecond, resources R1, R2 and R3 has already been assigned to P1. So I am repeating, there is a process P1. Okay. For a process P1 to execute completely, it needs resource R1, R2, R3 and R4. It needs all 4 resources to complete a task. But at time t equals to 10, so the process P1 has got only 3 resources R1, R2, R3. R1, R2 and R3 is held by the process P1, and this P1 is requesting for R4. But R4 is busy with another process P4. So R4 is assigned to P4. So it cannot be snatched. Okay? It cannot be snatched. Now, if this is the situation is some of the resources allocated to some process, P1 cannot complete the task until unless it gets R4, but R4 is busy with some other process. Suppose this is the situation, then P1 should release all 3 resources R1, R2 and R3. It should release all 3 resources so that R1, R2 and R3 can be utilized by some another process who is demanding it. It might happen that there might be some other process PI who is requesting for R1 and R2 and R3, just like R4 is being requested by P1. It might happen that R1, R2 and R3 is being requested by some other process in the system. So to use the resource efficiently, these resource has to be released. Now when P1 will complete its task or again begin its execution whenever it has got all the resources and all the old resources and all new resources. So P1 will again initiate the execution when it has got all the old resources, okay, as well as it has got the new resources. So this is the rule that you can impose on the no preemption. I'll just repeat it. Okay, if a process is holding some resource and requesting for another resource, which cannot be immediately granted or immediately allocated because it is being used by some other process, then all the resources currently being held by the requesting process has to be released. Okay, has to be released, which it has to release voluntarily. Okay, it's not that because you are imposing the rule. It should not that forceful snatching of resources from the process should be imposed. Not that. Okay, the resources should be implicitly released, voluntarily released. If you impose this rule, then no preemption will fail. Right? Now, when you release these resources, because it has not got R4 is not free. For P1, R4 is not free, so it will release R1, R2 and R3. So R1 and R2 and R3 will be attached to associated with list of available resource for use, so that some other process will be used. Okay. So now the requesting process will at the end the requesting process will try to have all the old resources and as well as new one to initiate the re-execution of the code of the process. Fine. So this is all about the no preemption. So next one is the circular wait. Circular wait is the last one. Okay. So just to make you a brief about it, what do you mean by circular wait? Okay. Circular wait means suppose there is a list of process noted by or denoted by P0, P1, P2 ... Pn. Okay. I repeat, this should be Pn. I have not added it so far. Okay, it's Pn, and there are a list of resource R0, R1, R2, R3, and suppose the system is entangled in a deadlock situation, and the list of process are P0, P1, P2 ... Pn. Then if this is the criteria, or if this is a sync, okay, some circular thing is there. Okay, R0 is assigned to P0, P0 is requesting for R1, R1 is assigned to P1, and then so on. Pn is requesting for R0, and so on. Okay, if circular thing is there, then this is known as a circular wait. Okay, so now how can I make the rules in such a way that what rules that I can impose in a system in such a way that the circular wait scenario fails? I repeat, what should be the rule that I can impose such that the circular wait scenario will get failed? Okay? So the rule is the rule is whenever you are requesting a process, or whenever process is requesting for resource, it should always request the resource in some organized manner. So I'll just repeat. Okay, I'll just explain it with the help of the example. Okay, suppose there are a list of process P1, comma P2, comma P3. Okay, P3. I'll have one more P0 also. P0, right? So it's easy. So I'll have, suppose I have got a system. In a system, I have got 4 process P0, P1, P2, and P3, and I have got 4 resource R0, R1, R2, and R3, right? Okay. Now the rule is, okay, these process P0 to P3, assuming only I have got this much amount of resource and process, whenever in a system, the rule is every resources is associated with some natural number. Okay? I repeat, every resources should be associated with some natural number. So say for example, some natural, any random number, okay, normal integer natural number. Say f of R1, R0. Suppose we have associated some natural number to R0. So the number is, say for example, 1. Okay. F of R1 equals to 2. See, you might go in increasing fashion or any abroad fashion. Somehow or the other, the resources should be numbered and organized in some increasing order of some natural number, like this. Okay, R0, R1. So you can reverse. Okay, you can reverse R0, R1, and R0. No problem. But they should be organized in some manner such that whenever a process is requesting, it also requests in some increasing order fashion. Okay. Next is R2, some any natural number. So, for example, I will give 5. Okay, any f of R3. Okay. So now you might be thinking, can I give 2 same integer value to the resources? No, you cannot give. Okay, answer is no. So every category of resources has to be numbered uniquely in some organized manner in increasing order, so that whenever a process is requesting a resource, it will request in some organized, in increasing order of fashion. Like for example, whenever a process P0 is requesting for P0 is requesting for R0, okay, but R0 is assigned to P1. Now P1 cannot request R3 directly. P1 cannot request R3. P1 has to request R1 kind. Okay. So this is the rule. P1 can request R1. Yeah, R1. So like that way you need to do. So if you do this, you will have the scenario of something similar to this. So you have this, okay? So you have this scenario, okay? If you follow this, okay, you have this scenario. Now, to make now we'll think the rule is this. You always assign some category of to the category of the resources some natural numbers, integer number in increasing order pattern, so that whenever process also requests in some increasing order. It should not happen that process P2 is trying to request for resource R0. It should not happen because P2 can P2 can request resource, any resource above R1. P2 can request R2, R3, R4, but it cannot request R0 and R1 because it's in sequence. Okay, so if you do this, you may end up with the situation that something similar to this. Okay, so R0, this is the scenario. Okay, so this is how you can make the request for the source. So R0 has to be accessed first and then R1. R1 has to be accessed first and then R2, like that, in increasing order. Okay, so if you follow this, so you will get this sequence, circular sequence. So Pn is again requesting for R0. So you will get circular sequence. Now, how this condition will become true? That is the big question. Okay? Now, to analyze this, let us assume that it is there. We will try to prove it by contradiction. Let us assume that in the computer system you have applied this rule and you have got this. I repeat, in the computer system you have applied this rule and you have got this. So this is true. Okay, fine. Now look at this. Whenever you look at this, okay, this is also true. So R0, you have removed all the PIs, all the process. So this is obviously true. Okay, and at the end Rn is again this arrowhead is continuing with this R0. Okay, because you have removed all P's. So this is true. So now you can see that R0 is less than R1, less than R2, less than R3, and so on. Rn minus 1 is less than Rn, and Rn is less than R0. Okay. Now, if this is true, by transitivity you eliminate this part. And you will get R0 is less than R0. So how it can be true? Okay. So it cannot be true. So if you apply this regulation, okay, then the circular sequence will never get encountered due to this mathematical scenario. Okay? So this is all about the circular weight. So this assumption is failed. So the rule is you give some natural number in increasing order of fashion to different categories of resources and ask the process to request in increasing order of fashion. If you do so, the circular sequence will never get encountered. So this is all about the today's class. So I just repeat it. So give you a brief about it. Deadlock prevention method is a method where you try to fail any one of the condition. Mutual exclusion condition is difficult to fail because of the nature of the because of the properties of the resources. Like for example, some resources, non-exclusive, non-shareable resources like printer cannot be made shareable, something like that. Okay. So this is one thing, and the remaining 2, 3, and 4, that is Holden weight, no preemption, circular weight. We have discussed certain set of protocol which you can apply to the computer system such that any one of these conditions fails. So you can apply any one of these conditions that I discussed in order to make one of the conditions to become fails. And if one of the conditions fails, then obviously deadlock will not occur. Thank you. If you have any questions,